sort of a first for me. I've not ever taught in a college environment. I've taught in the industrial environment. I've had students come work with me, and so we teach in a much smaller group setting. So this is a little bit different, but I'm quite excited. So our opening lesson is going to be just on the history and background of forging, what it is, and why we use it. And then we're going to get into some steel making. So today's lesson is kind of 4 independent segments. I titled the lesson, Forging the King of Crafts. Kind of as a little dig to Dr. Metzloff, since he's a profoundry guy, but also because it's true. So I'm going to use the first section here to talk about why that's in fact true. Before we do that, though, just give you some reference material. A lot of these references are out of print, but they're really excellent books that are available very inexpensively through the online used booksellers. So if you find that any of this is particularly interesting material to you, you can get your own copies. Alex has read several of these. When he was interning with me, I think he read Principles of Heat Treatment by Grossman. So he can give you his opinions, tell you which ones he liked and didn't like. Some of them are old, very old books like this one, which is available as a reprint. That one's not a metallurgy text, but it's great if you're interested in forging. Oh, hey, I like that. That's
There you go.
much
I
better.
can't see it on my
Yeah.
screen over here otherwise.
Thank you. So an outline of some of the things that we'll talk about. We won't get to all of these today, but eventually we'll cover them all. What is forging? What's it used for? How do we do it? What are the methods that are available to us? Steel making. Why we would use forging as a method of manufacturing, because certainly there are other techniques available. Casting, and today we have printing with metal, machining, lots of other things that we can do. So what's the value we get out of forging? And then different ways of forging. We've got open die forging, which is what Scott Forge really specializes in, and also closed die work, which is widely used for small components. And then we'll have some other lessons where we cover, the heat treat things that Dr. Metzloff mentioned earlier. So a little bit more about me. Yes, I did go to Ohio State, and like Dr. Metzloff, at one time Ohio State had a metallurgical engineering degree, and so I got one of those. They have since made their program much like yours, where you get material science degrees. After I graduated, I went and worked for the Timken Company at an R&D center in northeast Ohio for a couple of years. And then I've been with Scott Forge now for almost 16 years. When I was in college, I picked up blacksmithing and hand forging as a hobby. Prior to that, I actually was doing knife making. That's how I got exposed to metallurgy. I started making knives when I was in junior high school, learning about different kinds of alloys and heat treatments specific to that type of application. I found it fascinating and decided I wanted to go into that field. And then through knife making, I also got exposure to blacksmithing, and now I work in a place where I can kind of combine all my interests into a career. So if you're ever able to do that, take advantage of those opportunities. So I've got a few different images of me working in my shop, things that I've made. This one here in the center, right here, is kind of probably one of the most interesting things that I've done. That's a cell phone. It's forged out of a solid block of laminated copper. Now, when we break and I get out show and tell pieces, I've got an end cut off of one of those blocks. So that's copper, brass, and nickel silver, 3 different copper alloys that are laminated together, forged, twisted, and then flattened out into a block. And then the end user took that block and machined it so that it would accept the battery and the screen and all the buttons, and made a cell phone out of it. And they're a company that specializes in very high-end luxury goods, so they actually made about 130 of those. They've made some out of Damascus steel, they've made some out of exotic woods, all different kinds of things. So that's probably the most interesting thing that I've ever made. Oh, before I encourage you to ask questions. I will invariably leave something out, whatever it is we're talking about, without questions. So feel free to just jump in. If I don't see your hand, just yell at me. Because I want to make sure we cover everything that you're interested in. So what is forging? What's the definition of it? Well, it means that we're plastically deforming metal from one shape to another shape. Usually it's done hot, but it doesn't have to be. There's a whole subset of the industry that's geared towards forging at reduced temperatures or even at room temperature. But my experience is in the hot forging world, so that's what we're going to cover. And I talk about it as being the king of crafts because all other industries are dependent on forging and have been for millennia. When I was a student, I used to go to a foundry that was in Columbus. It's since been closed and torn down. It was a big steel foundry. It's been there for 100 years. I had a classmate that was working there, so we would get together in the evenings and do some studying there. And he took me on a tour of the shop one time, and in a maintenance building separate from where the foundry was, they had a whole forging setup with steam hammer and anvils and everything, because they needed forging technology to support their own operations. And that was typical for most every manufacturer years ago. Some things that I got in the illustration here. This is a closed die forging. This is a connecting rod for an engine. This would be a large shaft or spindle forging. And then over here we've got some fellows that are doing a hand forging demonstration of making an anchor. From an historical perspective, forging is probably one of the oldest methods of manufacture because you can take any naturally occurring metal that you don't have to refine and you can heat it up and forge it, or even not have to heat it. So for example, copper exists as a naturally occurring element separate from its ore. There are places in northern Michigan and other places around the world where you can go and find just a chunk of copper, and you don't have to do any refining to it. You can take that copper, you can pound on it, change its shape, make some useful utensil out of it. So copper, silver, gold, all of those things can be handled in that way. But when it comes to iron and steel, we see that steel, earliest iron artifacts go back to 3200 BC. Steel, which is a bit more complex to produce, goes back to 1800 BC. So these are technologies that have a very long and rich history. And the illustrations around these are, a lot of these are woodcuts from books that were produced in the kind of the Middle Ages or slightly thereafter, just showing how the technology was implemented at that time. Here we see a hammer. This is an older hammer that's been restored and is available for viewing in like a historical village kind of a situation. Those hammers were powered by water. You'd have a large shaft outside the building with a water wheel on it. They would turn this cog, which would in turn lift this, and this would just drop under the action of gravity. Or sometimes they would do what they've done here, put a big timber above it, which acted like a spring to force that hammer down more rapidly. And that kind of technology was used for hundreds and hundreds of years very effectively. A little bit more recently, we were getting into, say, the very early 1900s. So we've got changes in technology now, changes in fuel source. Here, you have coal used as a fuel source. Earlier on, wood, charcoal was used as a fuel source. What I'm showing you are images of people engaged in making chain. So today we use chains in industry all around, and it's made by essentially the same process, but it's been automated. But years ago, it was not automated, so an individual person had to make each chain link and forge it, close the end up and thread another link through and so on. I wanted to highlight the fact that on smaller chains, that work was done by women. And we often think of forging as an industry as a very male-dominated industry, and it is, it has been, but there were certain sections of it where women were had very critical roles. So you probably can't read that, but if you get online and download this, you'll be able to see the detail of who that person was and what she was doing. Over here, you see chain making done, I should say, this type of chain making was done sort of in the home. It's what would be considered a cottage industry, in that you'd have a house or a little cottage, and then off to the side you'd have a tiny little workshop, and that's where you would do your work. For larger scale work, you'd actually go to the factory. That's where the men would go. They'd go to the factory and be employed in a more factory type of setting, doing chain, again making chain, but much larger sections. And we actually have a video of that. Before we get to the video, here's a few images of the men working on larger things. This is a pretty neat picture because this chain that's in this picture is actually the chain that was the anchor chain for the Titanic. So they actually managed to get it filmed on photograph before the ship sailed. So now I'm going to need a little help to navigate to the videos that I want to show.
Little side note, my grandfather, who was a metallurgist to some extent, worked at Columbus McKinnon Chain Works in Tonawanda, New York. And I actually have, if you can show you how they forge weld these together, I have one of the samples of the first electrically welded chain links, and it's all labeled and everything. It's 1925 or something like that. 30 something. I'll have to look at it.
Yeah, that's
Okay.
the method for welding chain that you're going to see in the video, and also what Dr. Metzloff just referred to, is a solid state weld, where we think of welding generally being done as you melt metal through some kind of process and it becomes a filler metal. But these are techniques where there's no melting. You're just getting bonding through deformation. And we'll talk more about the mechanics of that later. The chain making was extensively done in England, and what's interesting to me is that even though those sort of what we consider modern manufacturing methods were developed in the 1920s and 30s, in England they were still hand making chain all the way up into the 1970s.
This one here?
Let's see. Yep, hand forging chain. Yep. So this film was taken, I don't know the exact year, but I think probably in the 20s. This is in England, and in a place, there's a region of England that even to this day is known as the Black Country. And that's where most of their heavy metal work was done. And it was called the Black Country because there was so much smoke that it was just black all the time. What's happening here is they've taken their starting material, which is wrought iron, which is different than steel or cast iron. And we can talk about the details later. But wrought iron, they've got bars that are hot and they're rolling them around a mandrel with that machine. You may have noticed that the ends of the bars have been sheared at an angle. That's to facilitate the forge welding process. So they make that, then they take it to a forge, a coal forge, and they swale away on it. Now, you might not be able to tell, but there's two men who are swinging the same hammer in that video.
Really? They're holding on to
They are holding on to the same hammer. It's a large hammer that has two handles coming out of it to allow for two men to swing at the same time. Yep. I've even seen pictures of some hammers that were so large they had three handles for this type of work. This here, this tool is called a swage, and they've got a lower swage underneath. They're contoured to support the round cross-section. They don't want to mar that because that would become a weak point in the surface. So they use shape tooling to accomplish this. And you can see that you have to thread one link into the next. Each of those links probably weighs between 100 and 125 pounds. So they're actually quite heavy.
That expression, the chain is only as strong as its weakest link, has a new meaning now.
Well, and
Every one of those is hand welded.
you're going to see in a moment how they give inspections on these chains. So what they're doing here is there's a cross stud that's being installed which helps keep the chain from twisting. Once the forging was done and the chain was complete, it had to be inspected because you want some reliability. So the way that they did that was they stretched it out on a big table, and you'll see in a moment that there's a bunch of the guys that are just hitting that with a hammer. And what they're doing is they're listening for the kind of sound it makes. And if that weld is a good weld, you'll have a high-pitched ring. But if it's not a good weld, it'll go thunk. So I was talking with the chief metallurgist for the American Bureau of Shipping, who I know, and I was talking to him about this. He says, oh, we still test anchors today basically the same way. They pick them up and they drop them. And if they ring, they're good. Now, we're going to go on to see forging an anchor here. This facility did both chains and anchors. So even though we're not specifically talking about anchors in our class, it's an excellent illustration of forging. It gives us a chance to talk about wrought iron as a material. Wrought iron was a very low carbon. It's basically pure iron, but it has a lot of slag in it, which is the result of the manufacturing process. The way they would do that is they would take cast iron, which has a low melting temperature, but very high carbon content, and they would remove the carbon by blowing an oxidizing flame over a liquid bath of cast iron. As the carbon content was lowered, the melting temperature would go up, and the furnace temperature was held to a spot just below the melting temperature of pure iron. So what would happen is you'd end up with solid particles. But the furnace was lined with sand, and the sand would tend to melt, and so you had iron particles in a silica, liquid silica, or actually iron silicate fluid. And so we just saw them pull a chunk out of that, and that's what was dripping, was the iron silicate. And then they would pound on it to get that into a uniform block, and that uniform block could be pounded against another block, and so on, and you could build up a large item from a whole bunch of relatively small starting pieces. Typically, those starting blocks would be roughly 500 pounds. So here you're seeing the main shaft of the anchor. Some things to watch for is you have that suspended by a chain, and instead of a machine, you have all these guys that are the machine to operate that. Now, Alex has been in our Ford shop. He understands what a manipulator is. That's the early version of a manipulator.
So what he's saying is that the actual shaft was added to one of those blobs at a time, and that's how they actually make the shaft.
Yep.
They don't make it in one big casting. They just add more material to it as they go along.
It was done that way because at the time, originally, they didn't have the technology to do large-scale steel stuff. And then when they did get that, there were still, at early times, there was still some advantage to using wrought iron in certain applications because it's pretty ductile. So you would see that in chain, particularly they wanted that in chain because you'd rather have a chain stretch than snap. And so stretched out chains may not be safe to use, but at least you can see that it's stretched and taken out of service before it actually has a catastrophic failure. Today we don't use wrought iron for anything. It's not even produced anymore, other than it's recycled. Blacksmiths will find it, recycle it, and use it for restoration work on old ornamental applications and things like that. But it's not an engineering material. Now here's what they're doing here is they're joining two pieces at roughly 90 degrees, two big shaft segments. One is the main shaft that the chain would be threaded through, and the other section is the arm of the anchor. And what you can see is that that piece is probably at around 2,500 degrees. It's almost to the melting point of iron, but not quite. The configuration of the thing they're making is so large that they cannot put it under a steam hammer. And we'll see steam hammers in other videos. So this all has to be done by hand. You can see they're bringing over these small bars and they're pounding them into place. What they're doing is they're filling up the space where the two major pieces don't fit perfectly. They can fill that in with those small pieces, and they'll go along and cut off the excess.
It's like a filler rod in your welding process.
Kind of, yeah. And then because they couldn't get it under a steam hammer, they've got a very large iron bar that's just suspended from the ceiling with ropes, and that's what you were seeing. They're just lifting and dropping it. This type of work is actually pretty challenging because if you don't get it quite right, you probably can't get it back into your furnace. So you have to get it right. You have to know that it's going to be right, have all of the people available to do the work in the moment. Otherwise, you miss your opportunity. Kind of where you get if you've ever heard the phrase, strike while the iron is hot, that comes from this industry. So now the major work is done, and they've got a large shackle that's going to be riveted in place. And so the rivet is a hot rivet. They're bringing it over from another location. The interesting thing to watch here is how you've got so many individuals that are working together in a timed rhythm. And you'll see that there's one guy who's kind of late to the party, and he jumps in, and no one misses any strokes. So again, this is the old way of doing things. We don't do work like this in industry anymore, but it does give you a nice perspective on the fact that how we could do, or people could do very massive things with limited technology, just because they had a drive to get it done. I was telling Dr. Metzloff before class started that I have a book that goes through a discussion of making not an anchor, but a large crankshaft for a big ship. The shaft weighed over 100,000 pounds, made by the same kind of processes of building things up, and this was back in the 1880s. They're talking about what's the best approach to make a forging like this, where it's going to take multiple days and a lot of these little blocks welded together to create this object that we need. So, any questions on the kind of historical perspective of forging?
How glad are you that you don't live then?
So, and that's just a little bit of the history of forging. There's a whole lot more that we can talk about, but I don't want to take too much time away from the core material in the class. What I'd like to transition to next is what industries use forgings. I made the claim that even today, forging is the king of crafts. So let's take a look at industries that use these. I've got them listed here, but I'm going to kind of move forward a little bit more rapidly because I've got lots of pictures to show different things that are being used in different industries. So start with aerospace. So by aerospace, I mean not only airplanes, but rockets, space shuttles, things that drive around on Mars. These are all things that utilize forgings. Here we have rocket nozzles. These are copper-based forging. Over here we've got aluminum forgings, we've got rings. Some of the things that we make at Scott Forge are connecting rings. So you're building a large rocket. It may be made out of, say, rolled sheet metal, but you've got to connect those segments together so that you're going to make a ring that will connect all these larger pieces together. Defense, that covers a wide range of forgings. Most of what Scott Forge is making for our defense industries have to do with things that go into naval vessels, in particular submarines, but also these up here, which are kind of neat, these are for aircraft carriers. If anybody's familiar with an aircraft carrier, you have the ability to throw a plane up into the air with a catapult, but then you have to catch that plane when it lands because you have a very short landing area. These are a precipitation hardening stainless steel, and they're the spools around which those cables are wrapped when they catch the airplane. Throughout industries, all different kinds of industries, there's a need for gears to transmit motion from one thing to the next. And so a lot of those gears are forged. These in particular are used in the oil and gas industry for offshore oil rigs that are used in relatively shallow water applications. So we're talking about a few hundred feet. In those circumstances, the rig, rather than being just a standalone floating unit, actually has legs that can be lowered down, anchored to the ocean floor, and will support the rig. And these are the gears that drive those legs up and down. This is just a sort of general catch-all category, general heavy industry. What you see over here is what we call an eccentric or crankshaft. So you've got the main shaft here, and you have a much larger diameter here, but the two are not at the same, they don't have the same center line. So this would allow you to make something go up and down. In the case of that particular forging, it's for a large press, where you just have a single item to be actuated. You could make something like that with multiple throws on it, and then it would become a camshaft or a crankshaft for an engine. That was not for that application, but they do make large engine cranks, say for locomotives, out of forgings in a similar way. Within the infrastructure world, we're talking about bridges, the ability to have a bridge that raises and lowers so you can have boats pass underneath it. What's being produced over here is a big arc segment. And that would become, actually eventually become a gear that will be used to actuate one of those bridges. That particular piece is kind of interesting because it starts off as a flat bar and then is allowed to cool, not down to room temperature, but to a point where it's not glowing anymore. And then they take that flat bar and they basically bend it by eye to get to that arc. And then they'll have a pattern that's been produced that they can check against, and they just keep working back and forth until they have the bend match the pattern that the customer asks us to work to. The mining industry uses an enormous number of forgings. I don't know how many of you may have seen mining equipment, either just because we build a lot of mining equipment here in Wisconsin, over in Milwaukee in particular, or online or television. They're sometimes featured in shows because the equipment is so large. This, to give you some perspective, so these are axles for a dump truck. If I were standing next to the axle, it would be as tall as I am. The wheel that gets bolted to this flange is about 12 feet in diameter. So those dump trucks can carry about 400 tons in each payload. They're made for Caterpillar. Komatsu has similar types of machinery. This long tube is on the order of 300 inches long, maybe 36 inches in diameter. and is used in the very large shovels as there's a proper name for it, which I don't remember at the moment, but basically the shovel is attached to the end of that, and that tube slides in and out, and is basically suspended in an enormous crane-type framework. I already talked about the gears that are used for oil and gas, but we also make things like this, which is a valve body. These are doors for a machine called a blowout preventer, which sits on the bottom of the ocean. You have an oil well that's drilled down into the ocean floor. You've got to get oil coming up out of that, or natural gas, or whatever the product of the well is going to be. You need to be able to control that. So there's a huge machine, like 75 feet tall, has a lot of different functions. These are components for that machine. Some of you may remember about 10 years ago, one of those machines malfunctioned. And there was a huge oil spill for an extended period of time in the Gulf of Mexico. The blowout preventer failed to do its job. What happened in that situation was one of the functions the blowout preventer can do is to close off the well in the event of a failure. What happened in that specific case was that the well pipe broke and fell down into the blowout preventer, which is supposed to have just one diameter of pipe in it. Well, it ended up with two in it, so when they went to kill the well, there was too much metal in there, and they couldn't pinch it off and keep it from leaking because of other problems that happened earlier in the event. So they're actually a quite important part of that whole process. And a lot of forgings are used in the oil and gas world. Power generation. So this here is showing you a way of making a component that gets used in a nuclear reactor. That would be, it's called a control rod housing. Up here, we have a large disc. That disc could be drilled full of holes and would become what would be called a tube sheet. And you put a lot of little tubes that would fit into those holes and then extend probably to a mating tube sheet somewhere else. And it basically becomes a big heat exchanger. But those tube sheets get hot, and so there's a lot of thermal expansion and contraction. They're quite large, so they're made by forging processes. This is a really interesting one, medical devices. So you probably recognize this as a replacement joint for a hip. Here's for a knee. Does anybody know what this is? It's a stent. Yeah. So what are stents used for?
For unclogged arteries.
That's right.
Blood vessels.
Yep. But I have it up here in a presentation on forgings. It's really tiny, right? It's going to go up inside somebody's chest and support their arteries. The reason I include it here is because the material that's used to make those little tiny wires is a titanium nickel alloy. Sometimes you might hear of things called shape memory alloys or superplastic alloys. Those are what we're talking about here. Those are made by an ingot metallurgy process where the ingots are somewhere between 8 and 14 inches in diameter, and they are forged. Scott Forges provides that service, and it forges them down to an intermediate size, and then they're sent back to the manufacturer where they're conditioned and then drawn down and eventually made into wire. But part of the manufacture of the stent is a forging operation. So, anybody like diamonds? Anybody wear diamonds? I don't have any. My wife has several. Right? You can make diamonds by synthetic processes. We're used to having diamonds, come up out of the ground. In fact, Dr. Meslop was just in South Africa. They're very well known for their gemstones. Right? Those are naturally occurring diamonds. But you can make diamonds in a manufacturing environment, and that's what you see here. This is a machine that's used to make diamonds. Now, the reason for doing it is because diamonds, besides having a lot of beauty and value as gemstones, are actually quite useful in cutting. And that's what these things are, all different kinds of specialty cutting tools. So it's cheaper to make them synthetically than to dig them out of the ground when you're trying to provide them for these kinds of applications. So one of our customers is the customers that build this equipment. So these forgings, big cone-shaped forgings, are things that we produce. Now, some of the things that get done at the research laboratories around the country, they're often looking at forgings for some of their work. This one in particular is pretty neat. These are wheels with a Mars rover that are made as forgings. They're aluminum forgings. So I'm really quite excited to be able to say that Scott Forge has forgings on Mars rolling around up there. Some other things, various kinds of analytical equipment. This one was made as a very large aluminum ball. That's probably about 3 feet in diameter. So we made it, a simple shape, and then someone else went and did a lot of complex machining to create a pretty unique inspection tool. This one here was let's see here, looks like a satellite component, aluminum, table aluminum hollow forging. This one, these are aluminum, again, aluminum. You can see that one of the things, and we'll talk about this more later, but the forging process allows you to make things that are relatively close to the final shape. We call it near net shape, or sometimes semi-finished. So these are, you can see we have a hole that goes all the way through. We've got multiple diameters all in one piece. That's one of the advantages of forging. We'll talk about that later in the lecture. That particular set of parts was used down just south of us, where they have a large particle accelerator. These are, applications that most people would never even think of, and yet we're using forgings to learn about, how the world around us works at the smallest level possible. Here we've got more of those copper forgings. And back to defense applications, that is a bomb, a specialized bomb for penetrating bunkers which are very, very, very deep underground. So I always found it kind of unusual that something that's a one-use item is going to need to be made as a forging, because it doesn't need fatigue properties, right? It's got one cycle and it's done, right? But the folks that design this are actually very interested in the mechanical properties, because, especially in this case, you have a lot of engineering that goes into the ability for this thing to penetrate a certain distance into the ground before it explodes. A lot of times when I think about explosives and bombs, I'm thinking of what I used to see in World War II films, where they're dropping, hundreds of bombs all at once, and they're either going to explode on impact or explode slightly above the ground. Here we're in a much more highly engineered situation, not only to get a certain depth of penetration, but also today we have bombs that are designed to be precision-guided weapons, so that you can target very specific situations, minimize damage to things that you don't want to damage, civilians, things like that, right? So the ordnance we have today is very highly engineered.
What's the top picture? Is that a cryogenic chamber or something?
Right, so that's being put through a cryogenic cycle to do some changes to the microstructure and properties. Yep.
Is that done like in-house, or do you have somebody else?
We don't really have the ability to do cryogenic stuff in-house. The closest we've come was actually, Alex was there. I don't know, Alex may have gone back to school before we did it, but I had some parts that I ran through a dry ice cycle. But that's not really a true cryogenic treatment. There's good reason to take some metals in certain situations and subject them to treatments that are in the -300, basically submerge things in liquid nitrogen. You can get some significant changes to microstructure and properties when you do that. Perhaps we'll touch on that in one of our history sections. I didn't put it in the lecture yet, but if you remind me, we'll cover it when we get there in a future lesson.
It might be something that you could do in your group project to improve the properties of the steel we're going to mess around with.
Yeah, absolutely. That could lend itself very well to that type of treatment. Here's another sort of research application. This was a big X-ray generator, used a lot of aluminum rings that we produced. So just in conclusion, the world around us everywhere is running on forgings, even to the extent of things that are in Mars. Satellites, rockets, submarines, which I didn't show, but submarines which go down to depths that they won't even tell you how deep they can go. It's classified. All of these applications have forgings. And more simply, and I kind of highlighted the big ones, but if you think about the things that you see over here, these are relatively small forgings. These are on our vehicles that we drive every day. They use forgings. So they're all around us, and they're critical. That's sort of, how do we forge? We talked about what forging is, we gave some historical stuff. But how do we actually carry it out today, right? Because it's not mostly guys with sledgehammers anymore. We have a few different approaches. One, which allows us to make what I call near net shape, but some other people might be easier to refer to as, say, semi-finished parts, is a method called closed die forging. So in this technique, you use a block of steel or some other material to create the negative of what you want, basically. And then you take your hot metal, put it in there, and when you pound it, the metal flows to fill all the cavities. Now, I say flows because it moves around, but it's not liquefied. This is a solid state deformation situation. Now, I mentioned that you can, most of the tooling would be steel. There's some fun exceptions to that. There are times when forging is done with the tooling at the same temperature as the metal being forged. And that's done here in Wisconsin over at a company called Laddish, where they forge a lot of aerospace components, things for jet engines, with fins and blades and things of that sort.
I'm going to try to get us in there, but we'll see. It's
I hope you
hard.
can pull it off. I've never been able to get in there.
I've been in there once.
Yeah. But what they use for that application is, instead of using steel, they actually make the dies out of blocks of molybdenum. Because the dies have to be at forging temp. So that means the die, if I normally forge steel at say 2300 degrees at my maximum temperature, which is what we typically do. Now maybe I'm not forging steel over there, maybe I'm doing something in titanium so the forging temperature is a little bit lower, maybe it's 18 or 1900 degrees. But still, steel at 18 or 1900 degrees is going to deform if I put a lot of load on it. On the other hand, if I use molybdenum, it will hold its shape. So that's what we use.
Those dies are like $1 million or something like that.
Oh, I believe it.
Yeah.
I believe it. So that gets to one of the key points about closed die forging. We're talking about $1 million for a pretty unique set of dies. Now that's not what this pair here would cost, but still, they are costly to produce because there's a lot of machining that's required to make these shapes in the steel. So therefore, you're only going to use this technique if you're going to make a lot of pieces and can spread the cost of the tooling out over many pieces. That tends to mean that you make smaller forgings by this method. Now, it doesn't have to be exclusive that way, but it's the general observation. Here we see tooling to make a connecting rod for an automobile. Here we see a forged frame for a revolver. Up there you see a chain hook. Here you see a crescent wrench handle. So these are common things that you often would find that the product, you know, even like I've got crescent wrenches, most people have crescent wrenches at home somewhere. They're forged by this method.
Anyone know how long just an average one of these dies might last? How many parts can you get out of one? I guess.
1,000,
Close.
1,500.
About 3,000 typically. That's what I've been told,
That's
plus or
probably-
minus a little
yeah.
bit. Now, they don't throw the die out and make a new die. What they do is they'll hard machine the surface of it deeper. So they'll just go and trim the top down a little bit, right? And then they can maybe do that. I don't know how many times they can do that, but
It depends on, you know,
Yeah, it depends on how thick the die is.
block is. And if they get to a point where they can't do that, they can always machine this out completely, and then they can flood weld that back with the, you know, and so that they're at least preserving whatever machining they did on the back that anchors that into the machine. One of the key differences between closed die and open die forging, which we're going to talk about in a minute, other than the intricacy of the tooling, is the fact that in most closed die type setups, the die itself is hard connected to the machine that's going to make it go up and down or side to side, however they're going to actuate it. It's permanently fixed, or, you know, I mean, they can unbolt it or whatever, but it's fixed. Yeah.
Do you have like sliding components in forging dies?
You can. I don't have any illustrations, but if you were to go out on YouTube and look up something called a Hatteber, H-A-T-E-B-U-R. It's a closed die forging mechanism, typically done with things oriented horizontally, and you could, and you're gonna, those are very high-speed forging machines where they're making a lot of small parts, like say for automotive components. So you can have a bar that's your starting stock, it'll go through an induction heater and be sheared, and then that little slug is put into the machine and it's impacted, and you get metal flow into the features that you want. And those are going to be operating at very high rates, so much so that they actually have to put special inspection in the line, because you've got, you know, a bar, standard bar length is say 20 feet. So you use up one bar, you've got the next bar coming through. The two bars are, you know, butted together, and you could actually have half of one and half of the other in the same slug that gets made into a component, but it's not really a good component, so you have to have a way to pull that one out of the line. They move so fast. Any other questions? Okay. So that was closed die. Open die forging is using really simple shapes. And this is a very classic example of an open die. It's a flat plate. A good way to think about open die is if you've ever seen a blacksmith, which you'll see this afternoon when we get down to the lab. That's open die. Simple shapes, simple tools. You can make a lot of different shapes with these simple tools, but they're still going to be fairly simple geometric shapes. So here we see 3 different diameters all in one piece, but they're all still cylinders. Here's a big disc. There's a big disc. You can make rectangular forms. You can do some other variations, but they're still simple geometric shapes. And that's okay if you're making something that's large, you only need 1 or 2 pieces. So the cost of making a specialized tool to get you closer to the final shape just isn't justified. And you can get close enough and then get your last little bit of work done with the machine. So the equipment that's used for open die work today is mostly large presses. You can use hammers, and we do still use hammers for small open die forgings. But anything of any significant size is done under a press. So this press that I've illustrated here is the largest one in the world that I know of. This is a 100,000-ton press located in Italy. And you can see, if you look closely, there's an individual right here. It gives you some sense of scale for this machine. A press of that size could pretty much handle any ingot that can be produced today anywhere in the world. The biggest ingots that I know of weigh 700,000 pounds. Excuse me, 700 tons. 700 tons is the biggest ingot that I'm aware of. And maybe there's bigger ones now. We're not producing anything of that size here in the United States, or even in the Western Hemisphere. All that type of work is done over in Asia. But variations on that, much smaller, are used all over the world. So in the company where I work, we've got presses that range from 750-ton capacity to about 16,000 tons. Before we had press technology, you did things with steam hammers. You saw a real short glimpse of one of those in the video that we watched earlier. We'll see some other videos that show that. Some of those steam hammers were pretty big. They had falling weights of up to 100,000 pounds. That's a lot of metal to have moving, rapidly. But you are really limited to how big a part you can make, even with a 100,000-pound falling weight hammer. So hydraulic presses, open die work, large parts, simple shapes, relatively low volume. When we want to compare hammers and presses, since they are both used, what we can see is that for a hammer of an 80,000-pound falling weight, that would give you the equivalent press capacity of about 2,000 tons. So in the shop where I work, we have a 2,000, 2,500-ton press. We can work stock on that press up to about 40 inches in cross-section, maybe 40,000 pounds. So those are big parts, right? But that's nowhere near the biggest stuff that's being produced. Also, as just an interesting side note, if you're trying to figure out how to efficiently use your equipment, you can assume, and this was a historical recommendation, that for every 1 square inch of cross-section you had, you'd need 50 pounds of falling weight if you were going to efficiently work that metal all the way to the center of the cross-section. So you can see that you pretty rapidly get, if you're going to make big things, you pretty rapidly get to the point where you either have to have hammers that are just so large that it really can't be produced, or you have to go with hydraulics. So another variation that we have in forging world is called radial forging. I'll show you an image of what that is in a minute. Radial forging is used for long products. They can be bars, it can be hollow forms, it can be parts that have multiple diameters, but they tend to all be round, they tend to be long. There are some materials which lend themselves to this forging method better than a conventional open die method with just done between plates. Certain very high alloys, say some super alloys, nickel super alloys, things of that sort. The difference is that instead of having two plates that move or that work against one another, you actually have four. And it's not a great image, but you can see here, here, and down here, and then there's one behind the bar here. Those four dies are actuated simultaneously, so that you're always putting a compressive load on the part from four directions at 90 degrees. That has the advantage that you will never create a shearing action in the center line of the part, which could be problematic. We'll talk about that more later. So you're always putting in this compressive work. Over here we can see a lot of different shapes that can be made. Here's a hollow form that has multiple diameters, both in the OD and the ID. So all different kinds of applications. But this is particularly suited for long, skinny kinds of components. Whereas the open die work that I showed before, let's see if I can do it backwards. By showing something like this, you can make long, skinny components with these tools, but you can make a lot of other things as well. So this type of setup gives a company sort of maximum versatility. Now, we also have a variation which called ring rolling. This kind of falls into the open die world. I showed some images of large rings earlier, just as kind of products that are produced by forging. Ring rolling is done to create a ring form that, well, rather than me tell you, I want you to think about how else could I make a ring? If I just was looking to have a ring shape, how could I do it? I could make it as a casting, sure. It's a legitimate way of making it, absolutely. What else could I do? Yeah.
Machine it?
You could machine it, sure. Yeah, anything else? There's at least one more method to make a ring.
Well,
You could weld it, right? So what would you do in that case?
bend it into a circle and mold it.
Bend it into a circle and weld it, right, absolutely. So those are, you have four different ways that you can make a ring. If we think about the method that you just mentioned of welding it, as compared to this method, why might we choose to go with this method of making the ring where there is no weld, as opposed to welding?
Way stronger.
It's stronger. Okay, you want to expand your answer a little bit?
Welding does all sorts of weird stuff in microstructure,
Okay.
so it'll definitely be more uniform when you want like a single hard spot or soft spot for the piece of pipe.
Good, good, yeah,
When you weld something, you make you make a sort of interface.
yes.
Whereas if you just forge it, you don't have to have an interface to deal with. It's just one continuous.
That's right.
So like,
And that is the primary reason for making a ring by this technique, is you have uniformity of properties all the way around. So if I'm going to make this ring eventually into, say, some sort of a gear, for example, where there's going to be high load on the gear teeth, there's going to be wear on those teeth, I want the confidence that I'm going to have uniformity of performance all the way around the ring. So at this point, I would like to show another old video clip.
okay.
I'm just going to need Dr. Metzloff to help me set that up. What we're going to see here is making a ring where we are in fact welding, but the guys are in this are doing a solid state weld, just like we saw when they were making the chain. So you have not the same type of disruption that you get in a conventional arc welding component. But this one was made by this technique because they didn't have any other options. you couldn't do what we do to make a ring today, make a big cylinder, punch a hole in it, and then stretch it out. That technology didn't exist. So what you're going to see, this video and all these videos that I'm showing, with maybe the exception of something that's unique to Scott Forge, these are all out in the public domain, out on YouTube. What you're seeing here is another. Is this the ring one, or is this? Oh, this is the steam hammer one.
What's that?
This is another video. Can we save this for later?
Oh, that was Westinghouse, yeah.
Yeah.
Okay.
They're filmed on the same facility, I think, but different regions, different spots. Different.
What is it?
It's welding the big. It's this one here, 2232 S1. So what you're seeing here is a ring that's being made where they've taken a bar, they've bent it on edge, and they've got a joint to be made. But just like with the chain that we saw earlier, where they had a tapered joint, they've done the same thing here with the tapered joint, overlap, and now they're heating just that joint, and they're going to hammer on it and weld it together. This was filmed in 1904. This was filmed at Westinghouse. So some of you may have heard of the company Westinghouse. I'm not sure if they're technically in business anymore, because they had some difficulty with some big facilities they went to build. It took way longer than they should have. So I'm not sure if they're still actually in business or.
They make turbines and stuff like that, didn't they?
Well, they did, yeah, they did, and they made nuclear power plants and things like that, and they had some that went way over budget not long ago. So I'm not sure if they're still in business under Westinghouse. But at this time, they had, of course, their own company. They had their own manufacturing, which is what you're seeing here. This is particularly interesting to me because at Scott Forge, Westinghouse is a customer, or was a customer of ours, and we made rings for them very similar in size to the one you see here. So you get to see the 1904 way of making it, and then I'll show you a clip in a minute of how we would make this ring or similar ring at Scott Forge. This is always fun for me to show at work because we have a very strong safety culture where I work, and of course you can see that is very lacking in this workshop. So the guys are all very aware of all of the safety gear that's not present in this video. Well, in the second clip, this is a 2-clip video, you'll see that one guy does get hit with a hammer, and he keeps working. He gets hit in the shin. But when you think about what's going on there, not only are there a lot of safety things, but the physical effort required to produce that part is just sort of phenomenal. And just, it wouldn't even happen today, I don't think. There's not very many people in the world that can even do this. Well, I shouldn't say in the world. Yeah, I mean, they can do it there, but certainly here in the States, it's going to happen. This is a fun video for me to watch as a blacksmith, too. I enjoy watching what's going on in the background, because there's other crews that are doing other work. And you can't really see any of the other projects that are being worked on, but you can see that there are other teams of men working, and it's just impressive to see the stamina that they have for the work that they're doing. So in the second clip, what you're going to see is they will take the ring out of the fire, and they're going to take it to a small steam hammer, where they're going to pound on it some more. The reason for doing that is because the region that they've welded is actually a little bit thicker than the rest of the ring, and they need it to be uniform. So the steam hammer allows that to happen pretty efficiently. When they do that, the metal on the edges of the ring is actually going to expand out a little bit, so that in that region you'll have basically kind of a flare. They need to trim the flare off, and you'll see that here in just a minute. Just as a side note, there's an operator who's making the hammer go up and down, who's behind the hammer, you can't see him. There's the guys who are holding the ring, and then there's this other fellow who's holding onto the tools. So they all have to work together as a team. So what he's doing right now, and you can't see it very well, but he is holding some curved cutting tools that are being used to trim the flare off the inside and outside of that ring.
It's like a knife.
Kind of like a knife, yeah. But he can't go all the way through, because if he did, he would smash that tooling right down into the lower die of the hammer. So he trims most of the way through, and then they swing the ring back around to the anvil, where they trim the rest of it off using a hand tool, which looks like basically like an axe or a splitting maul that's being struck by a sledgehammer. And it's in that, or near that process, where the man swinging the sledge misses what he's swinging at and hits his coworker in the shin. No?
Rather the first one than the second.
Yeah. This is,
I have now.
you have it now. You have it now. Like I said, all this stuff is out. This is on the Library of Congress website. It's very much public domain material. From a historical perspective standpoint, most of the guys who are in this video probably are immigrants. There was a lot of, at this time, a lot of immigration from places like Ireland and Eastern Europe, and those cultures had very strong metalworking traditions, so you would see a lot of immigrants. And even today, if you go down to Chicago, there's some very large Polish neighborhoods down there. In fact, even at Scott Ford, we have one of our facilities is in that area, and there are folks that work for us who speak Polish as their first language.
Good.
Mm-hmm. Yep. 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 We've got one fellow he grew up in Poland and he had forging classes in high school. He told me about making a knife in high school. Part of his metalworking training. Yeah. What?
Should still be doing that.
Yeah. Oh, absolutely. Now watch carefully. And fellow gets hit.
The eyes and the man.
Something, yeah. Yeah. It's kind of amazing, you know, we've watched about, what, maybe,
There's the manager there.
yeah, the guy in the bowler hat. Yeah. You know, we've watched maybe 15 minutes of select clips today on these historical things. And in that time, we only saw one guy get hit with a hammer. And think about how much time was spent swinging hammers to get that work done. It's kind of surprising that they didn't have more. I'm sure they did have quite a few injuries because they really didn't have much for safety culture, but you know, it's kind of surprising we don't see that more often. Now, there's one more video clip I want to go to. So now we're going to take, let's see if this one is the one. And so now we're going to see the modern way of making a ring. This video has kind of been a little bit sped up, I think, to keep the size down. So it's not really a real-time video, but it still shows you the process of how we would roll a ring. This is filmed at Scott Forge. I'm sure you could find other videos of ring rolling out on YouTube. They're all going to show you basically the same thing. What you don't see in this video is the precursor steps of making a cylinder and putting a hole in the cylinder. You can see we've already got a ring that's been formed on the press. They bring that small ring to the ring rolling machine. The ring rolling machine has two mandrels, one in the ID, one along the OD, and then you've got these two cones that are on the top and bottom. The cones are used to control how tall the ring gets, and the two mandrels control how thick the ring is, and really, ultimately, what the final OD and ID are on the part.
Now he's spraying that water on to get rid of the scale.
Right. Yep. So scale is another name for iron oxide, which forms rapidly at high temperatures. So in the world of forging, you have to manage that because you don't want that embedded in your workpiece. That's going to be all stuff that has to be machined away. So that was kind of a super fast video, but it still shows you the basic process of how we would do that. Our equipment will allow us to, and that's the end of that there. So our equipment will allow us to roll a ring around 20 feet or so in diameter and up to about 80,000 pounds. There are other ring rolling machines in the industry that can go larger than that. Any questions so far while we get back to the slides? All right. So we've covered ring rolling.
So generally, from a test standpoint, you know, each one of these processes would be, you know, something that might show up as test questions, something like that. Okay, kind of understand what each thing is.
So we've covered, now we've touched on history, we've touched on method. Now let's talk about why. Why bother, right? We already talked a little bit about you could take and bend a ring and weld it, but that might not be good in all cases. There's several different reasons why you would want to consider forging as a method of manufacture. And cost is an important one. Buying a forging, just go buy a forging, is not cheap. But it still may be cheaper than the alternatives that are out there. If we think about the comparison between the open die and the closed die forging that I talked about earlier, we've got tooling costs. But that's also true if you're going to make a casting. If you're going to make a casting, you first have to have a pattern. Depending on how intricate that casting is, you may have to have cores to go with the pattern. So there's essentially the same types of tooling costs associated with making a casting as you have with a closed die forging. So that's fine. The casting may be perfectly suitable for the application, but if you only need one or two, it may not make sense to go through all the cost of having the pattern to create. Another very important thing is that if I were to compare the amount of time to machine a part, if I take just a block or a big bar and I want to machine a shape out of it, I can do that. We have the technology, we have big machine tools, small machine tools, we can do that. We may be even able to do that kind of somewhat quickly, but we're not going to be able to do it as fast as we would be able to take something that's already, say, 80% of what you need is already there in shape before it gets to the machine tool. So you have reduced machine time. When we think about some of the machining that goes into some of the things that we make at Scott Forge, you might have multiple days worth, and by that I mean 2 shifts of 10-hour shifts. So you might have 80 or 100 or 150 hours of machining, or maybe even more, into a single part. And that's after it's been forged. So if you think about trying to do that without the benefit of forging, your machine time and the cost associated with it goes up astronomically.
What are you guys quoting out machine time at, you know?
I'm not sure what the
It's over $100 an hour, probably more like 100 and something.
Yeah, I mean, each production process has its own,
Yeah.
own cost associated with it. But overall, if you were to look at the overall cost of manufacturing, yeah, that's probably somewhere in the ballpark anyway. I mean, I think they don't charge by the hour, they charge by the minute. So you figure out how many minutes it's going to take you to machine something or forge something. So, forge minutes might be $20 or $30 or $50 a minute. Machining minutes may be $2 or $3 a minute, but if you've got 100 some odd hours of machining, it adds up fast. This middle one is really important. We're going to talk a lot more about that in a little bit, but this idea that you have freedom from internal holes. So you make a casting, you go from liquid to solid. When that happens, the liquid metal shrinks, which results in cavities inside the casting. Now, a well-engineered, well-designed casting will have those holes limited primarily to the gates, the runners, the risers. It will try to keep them out of the final casting. That's not always feasible, and one of the things we've heard from our customers is that the quality of castings in many industries has gone down over time, because a lot of the knowledge to create a really good casting has been lost as people with that expertise have retired out of the industry. They haven't been able to recover that. And so what's happening is that many of our customers are coming to us and saying, we used to get these as castings, but we can't get new castings that don't require weld repair on every single piece. And we don't really want to do that. We're willing to pay more per piece for forging, because in the end, by the time we have a finished component that goes into whatever the thing is that we're making, the overall cost is actually less. So we also don't want those little holes in castings that are there not only because of repair work, but because they can be initiation sites for failure in service. And so a properly executed forging won't have those. Now, I'm going to say that if you don't do forging right, you can have those holes remaining, and that's a problem just as it would be if it were in a casting. Here we have anisotropic mechanical properties. So this is particularly good when you have items that are loaded in fatigue. So I showed those axles before for the giant dump trucks. That's a fatigue, that type application. You've got an empty truck and then a full truck. You've got bumps you go over and maybe a smooth road. That's fatigue. And forgings, because you're able to force the metal to flow around features, will give you enhanced fatigue life. And then finally, we have the ability to control microstructure properties. There are some materials that develop their mechanical properties only through plastic deformation, as opposed to, say, through just a thermal process, some sort of a heat treatment. So we're able to do that on the forging side. Any questions? A bit more on the cost, just to sort of put some, actually, jump to this image here, just to put a picture with the description I gave before. Again, for a sense of scale, you can see the blacksmith on the right-hand side. This is on a 5,500-ton press. Not sure what the weight of this forging is, but you can see that if you were to just make a big round bar, a big cylinder, you could do that, but you'd have to invest a lot of the time in machining that away. And not only would you have extra time, but there's a cost to the raw material, right? If you were to, sit down with pencil and paper and figure out how much material you would have to turn into machining chips to do that, you see that it's significant. And if you assume that on the average, the cost of raw material is, say, $1 a pound, which is probably about right, that's a lot of wasted money if you're going to just turn that into chips. We just took a break. Anybody need a break right now? We can stop if we need to, otherwise we can just keep going. Keep going, all right. So I want to transition into something a little bit different now. We want to talk about this idea of the anisotropic mechanical properties. But to do that, we need to talk about microstructure a little bit. And we're going to get into what we call grain flow. So in forging, we are taking the product of the casting process and we're changing it. Casting process, we're going from a liquid to a solid, and so we get solidification. In that process, you go from liquid to solid, which is liquid to crystals. In the case of metals, we form crystals. Those crystals we call grains. Depending on the cooling rate, these grains can have a wide variety of sizes and shapes. Dr. Metzloff and I were talking earlier, and I'm sure we'll come up again about in the case of the WOOPS material, that you get crystals, some of them which are so large that you can see them with the naked eye, and that's actually how we get the patterns in those materials. In a more conventional process, if we're making an ingot, which is really just a big block of metal, you pour metal into a mold, it's a very simple shape, and you let it solidify. That's an ingot. When you do that, you get three distinct regions from a microstructure standpoint. You have right near the mold wall, the metal that's very first to solidify, that's going to have a very, very fine crystal size, or grain size. And those are going to be equiaxed, basically round, if you will. But then as you move further in, you'll start to have grains which are, we call them columnar. They have a very distinct radial arrangement. And then at the very center of the ingot, the last metal to solidify is, you're going to have, again, equiax grains, but they're going to be quite large. You'll also have, it's not illustrated here, it will show up later, in an ingot you will also have holes that are oriented down the center. That's where the shrinkage, in a casting we call shrinkage cavities. In an ingot they're sometimes called pipe. I think shrinkage cavities is probably a more technically correct term. But all ingots will have those features to some extent. Sometimes they're quite extensive. That's important for us as a forging person to understand, because we want to make those go away eventually. We'll get into how that's done. We need to understand how those things form first. So here's some cross-sections of various ingots. This is a transverse cross-section of some copper. You can see the columnar grains that are oriented radially. Here we see a longitudinal, and what I mean by that is they've sectioned the ingot lengthwise. So here you can see, again, columnar grains, and then going into equiax grains in the center. Same type of thing in this ingot here, and at the top we can see there's a big cavity there. That's the shrinkage cavity. And that particular ingot, that was open to the top of the ingot, or open to the surface. Usually in the world of steel, the ingots are designed such that those are not open to the surface. And I'll explain explain why in a little bit. Here's a cross-section of a larger ingot. This is more of what we would expect to see in the world of steel forgings. We have some distinct regions. Not shown right here is the very bottom of the ingot. The opposite is the top. Ingots in the steel world are cast vertically. And they're, not only are they cast vertically, but they're cast in such a way that the metal flows in at the bottom. Again, we'll cover that in more detail in a little bit. But you have, the important thing though, you have a distinct top and bottom, and those regions are typically discarded. The top is going to be the last area to solidify. That's done by placing either insulating or exothermic materials at the very top of the ingot to force it to cool the slowest. And because it's the last region to solidify, it tends to have the highest concentration of non-metallic material, and therefore we discard it. Again, we'll cover that in more detail later. Any questions before I move off the slide?
We plan on making an ingot, so some of the casting folks that are taking my casting class, we need to kind of get our heads together and figure out how we're going to make the ingots so it can cast some steel into it. We've got to figure out the alloy and everything, and then we'll go through this whole process, hopefully successfully.
Yeah? Yes?
Did you say that the metal is inserted from the front?
It is.
How is that done?
Well, I'll show you in a minute how that's done, and I'll talk about why they do that as well. Again, taking a historical perspective, it used to be that you would just take and pour the metal right into the top of the ingot, right into the open mouth of the mold, and let it fill up. But that tends to result in a dirtier steel, one that has more, in particular, more oxide inclusions, which doesn't give you the best performance in certain, so the technology is advanced. So we take that ingot, which has those varying grains, some quite large, has holes inside of it, and we put it through a deformation process. Now, I'll say that you could deform an ingot without forging it with a press or a hammer. You could use a rolling application. That's what most steel mills do. They use big rolls to take ingots or products of a continuous caster and squeeze them and shape them. Their goals are basically the same as what we have in the case of forging, but the end product is going to usually be a different shape or different size. But in both cases, what we're trying to do is take that as-cast structure and characteristics and change them. And we want to change them pretty significantly. We're going to take those grains, we're going to make them much smaller, we're going to stretch them out, we're going to allow them to become much smaller, and in doing that, we're going to stretch the ingot out along its length. And by doing that, we get properties that are different in the long axis or the longitudinal orientation than we have in the transverse orientation, which would be 90 degrees to the long axis of the ingot. Or it would then eventually be a forging or a bar or even a plate that's coming off of a rolling mill. So that difference in properties is related not only to the change in microstructure, but also to the fact that you're almost always going to have some amount of non-metallic material in the steel. We can talk about why that is a little later, but just accept that it's there, and those non-metallic particles can be stretched out and elongated a little bit like taffy. And that is why you get a directionality and properties. But we can take advantage of that, so if we're making a forging, we can forge our shape and force the metal and the non-metallic material to bend around a feature of some sort, like the big flange on the axle, and thereby giving us better properties, better fatigue in that area. We'll have a little bit more, hopefully, we've got some other illustrations that I hope will make that clear. So I mentioned these two terms, longitudinal and transverse. Longitudinal, parallel to the primary direction of grain flow, or the primary direction of elongation of the material itself. And transverse is at 90 degrees to that. If I'm going too fast, let me know. I see some people are really rushed to take notes. I don't want to go too fast.
We'll also have this PowerPoint on Canvas as well. This is kind of like your microstructures, if you've taken the class that deals with microstructure polishing, a transverse versus a longitudinal section through something.
We can use metallography to establish what direction something has been processed in by looking at the grains, looking at the, in particular looking at the micro inclusions and seeing how they've been stretched out. And that allows us to sort of backtrack. If we don't know, we can go find out how that did. Okay, so moving on. As an illustration of this, and again, bringing in a little bit of a historical perspective, we talked about wrought iron just a little bit when we were looking at the chain. And I mentioned that wrought iron is really a combination of iron, pure iron, and a slag. So the slag is an iron silicate. So what you would have if you had wrought iron, if you were to look at that, say, under a microscope, it would almost look like a composite material. And that's probably the best way to think about it today. It's really a composite between a metal and a non-metal. Because that slag was so thoroughly mixed in with the steel, or the iron, excuse me, if you were to break that piece, it would break and it would look like this. This is a piece of wrought iron that's been sawn about halfway through and then bent. And it bends and it kind of breaks much the same as a piece of wood. If you took a tree branch and you tried to break it, it often is going to be very splintery. It's not a real, it doesn't look like a sawed surface. It's all splintery. So we use wood, which I've just got a simple block of wood there, as an analogy for what's going on in the world of metal. Because metal has a distinct orientation, we can see that the wood sort of, I'm actually going to jump forward one slide, it kind of gives us a good comparison. If we imagine a test specimen that's oriented, let's say it's a tensile test specimen, right? So if that's oriented in the same way as the main grain flow of our piece of wood, we would call that longitudinal. And up here, we've changed the orientation of the specimen, so now it's at 90 degrees, the orientation of the piece of wood. Now, I tried to use this illustration yesterday with a young man who's my intern, but he's from California, and he's never split a piece of wood. He had no idea that people actually heat with wood. This is how I heat in my house. How do people not know this? So, is this a good illustration for you guys? Okay. So if we take a piece of wood that we want to split, we know we can orient that a certain way and it will split fairly easily. If we try to drive an axe through it the other direction, it's not going to split at all, right? So the same thing is true with a piece of metal. I can orient it in a way that's favorable to crack propagation or failure, or I can orient it in a way that's not very favorable to that. And so we see that if I look at just this, just to imagine a cylinder. Here we have some tensile test specimens that are illustrated. This one is parallel to the grain flow, and these two are both perpendicular. And again, this is a different shape of a flat bar, but the important thing is to see that we have the direction and elongation of the part, in one case parallel, and in this case perpendicular, to the way we're going to actually load that specimen when we put it in the test machine. So here's a picture of actual tensile specimens that have been broken and how they differ. This one was pulled in a longitudinal orientation, and this one was pulled transverse. We can see a few things. First, this one's a little longer than this one. It stretched more before it failed. This one also, it reduced its area. We call that reduction of area, of course. That parameter, it reduced its area much more than this one here. This part here, we call that ductility, the ability to stretch before it breaks. So in the longitudinal orientation, you have typically greater ductility than in the transverse orientation.
But if you're just doing the tensile strength, they're not much different.
That's right. That's right. That's a key point. So if you're just looking at the yield strength, how much load can you put on that specimen before it starts to permanently deform, or the ultimate tensile strength, how much it will take before it actually fails, those two values are typically pretty similar regardless of orientation. It's really the ductility and the impact properties that are orientation dependent. And here's some microstructure. You can see here we have some of the non-metallics. These are manganese sulfides. And we see in a longitudinal orientation they're stretched out much like the grain in that block of wood. And here you're really looking at the end view of one of these little stretched out bits. And this is why we see that orientation dependent behavior. Here's sort of a macro view of what's going on. We've got some, an old anchor component. Here's a flange, like a wheel flange. This is a hammer. But what you can see that in all these cases, they've been etched, or at least allowed to rust significantly, so that you can see the grain flow of the component. Here's a sketch of a connecting rod, and we can see if we make this connecting rod and we forge in the hole, we get the grain flow going around this way. Whereas in this situation, if I just machine that out of the block, there's no preferential grain flow. And so I would be at somewhat elevated risk of having a failure through this region that would be reduced in this method of manufacture. Any questions on grain flow, longitudinal, transverse orientations? It's a subject that I deal with a lot because we have things that are tested. Customers want that as a regular thing, and they sometimes want one over the other, or they want both, or they want both to reach some minimum value. So that the concept of grain flow and mechanical testing is really a pretty big part of what I do as a metallurgist. There's a lot of other influences that go into that, which we'll get into in some later courses, but I feel like I've only given it just a little bitty, very brief discussion. I'm not sure if I've covered it in enough depth, so please ask any questions you may have, or Dr. Metzloff, if you've got some.
I have a piece of wrought iron here. I think it is. I think this came out of a rivet from a ship. Then I put it through a rolling mill. But if someone wants to actually take and polish a transverse section and a longitudinal section of this, you're welcome to cut a piece of this off. The reason why I flattened it like this was to do pattern welded steel, because wrought iron, because it has that slag in it, when you forge weld it, the slag oozes to the surface and protects it from oxidation, so you don't have to put separate flux on it. That's why in the olden days that you could, a blacksmith could weld two pieces, solid state weld two pieces together without having to put flux or worry about oxides on the surface so much. So it's a pretty cool material, even though it's not made anymore. And by the way, if you find a pile of this somewhere, it's worth a lot of money. If someone's going to scrap an old truly wrought iron bridge, let me know. We'll cut it up and we'll sell it in little chunks to blacksmiths.
Yeah. Blacksmiths will pay a premium for that stuff.
Yeah.
That's true. Yeah.
How does grain size compare to castings or forgings? Because I know they're really long, but are they similar to like really small refined grains and castings, or are they like?
So the grain size, the actual grain size, is going to be very small. Typically, grain size is usually measured on an ASTM grain size scale. In the world of forgings, you're typically going to see requirements for the grain size to be 5 or finer, 7 or finer, and it's not unusual to see them much smaller than that. But those are typically what customers are going to require. I don't know what the typical output of the casting process would be, but you're going to definitely see them being equiaxed, and you're going to see in a casting, you're going to see properties that are basically the same no matter how you orient your test.
Yeah, so that's the main difference between a forging and a casting. Besides, let's say there's no porosity in the casting. The casting will have isotropic properties generally, same in all directions, whereas a forging will have enhanced properties in one direction and maybe the same or slightly lower cross direction. So if you got something that you're only going to pull in one direction, that's a good idea to make it as a forging if you need that extra strength.
So there's another section for the lesson that's about, we covered about 2/3 of the material that I had prepared for today. The last third is all on steel making. We can do it now, but I see that we're...
Let's do the demo, I'm
So
thinking.
we'll stop for today on the
Yeah.
lecture side.
We can move this all around and we'll readjust.
I kind of thought that might happen, so I'm not
Yeah.
surprised at all.
I'm going to do roll here real quick. Then what we can do